We start off with some data contained in matrix X, which we want to compress into a single column. Each row represents a point in space. The first column represents one variable, while the second column represents another. To compress each point into a scalar, we consider the direction of greatest stretch. The greatest stretch is the largest eigenvalue of x transpose x. We plot the eigenvector associated with this eigenvalue. We orthogonally project our data onto this vector. The distance the projected point is along our eigenvector will be the scalar representation of the point. We can find these distances by rotating our data onto the x-axis, which we will use to measure the data's distance from the origin. These scalar values form the first principal component. We have compressed the information from two columns into a single column. Since we started with only two columns of data and we now have a single column of data, we'd normally stop here. But let's look at what happens if we try to extract a number of principal components equal to our number of columns. We find the unexplained variation in the data by taking the difference between our original data and its projection. We put the tails of these unexplained variance vectors on the origin. Note that these vectors all fall on the same line. This direction is given by the eigenvector of x transpose x associated with the smallest eigenvalue of x transpose x. Because our data is already on the vector of greatest stretch, we are ready to record the distances of each point from the origin. Again, rotate the data onto the x-axis to find each point's distance from the origin. These distances form the second principal component of our data. Removing the explained variation from the data, we find that all observations are now on the origin. We've explained all the variation in our data.